Hello, good evening, everybody. Thank you for coming to this 11th lecture of our public astronomy series. My name is Shuda Mao from Center of Astrophysics here. Today I'm delighted to have Professor Brian Schmidt, the president of the Australian National University, to deliver a lecture. Brian obtained his PhD in 1993 from Harvard University, where I first met him. He then moved to Australia in 1995, forming his own supernova search teams, which led to the surprising discovery in astronomy about the accelerating universe. For this, he has won numerous prizes. I think I only need to name one, that is the 2011 Nobel Prize in Physics. I should also mention that Brian has made important contributions to the collaboration between China and Australia. For that, I'm grateful to him for his involvement in the bilateral collaborations between the two countries. Without further ado, I introduce you to Professor Schmidt to deliver his lecture. Let's welcome. Please.
Thank you, Shude. And thank you, everyone, for coming out, especially those students doing their exams this week. I greatly appreciate it. So today, I'd like to tell you about 3 big questions for astronomy. But these are not the only 3 big questions. They're just 3 questions that I think are particularly interesting. So there is much more going on in astronomy than what I will tell you today. But let's think why we do astronomy. We do astronomy because it's interesting. And we've been doing it for a very, very long time. This is a star cluster known as the Pleiades, at least the Pleiades in English. They've been around for 80 million years, and every human that has ever lived on planet Earth has seen these stars because they're visible from the northern and the southern hemisphere. I grew up in Alaska, very far north. I could see them there. When I go down to the southern part of Chile, I can see them there. And every culture, including Chinese culture, has referred to them. But I'll take you to one of the oldest pictures that we have, which is this one, in a cave from France, 17,300 years ago. And what you see here are the Pleiades, the 7 sisters, as they're called in many cultures, not Chinese. And they're sitting next to this animal, this bull. Why? Well, in European culture, that bull is known as Taurus. 17,300 years ago, we called the constellation in Europe the same thing we call it today. The 7 sisters, or the Pleiades, are referred to the 7 sisters all over the world. Not everywhere, but in the stories of Aboriginal Australians, they're referred to as the 7 sisters. The Aboriginal Australians came to Australia 40,000 years ago. And that is the same story of those same stars that occur in Thailand, occur in India, and occur in Europe. These are the oldest stories that we know of humanity. So, astronomy has been something humans have been thinking from as long as we can imagine. Today, I was with my Prime Minister at your ancient observatory in the middle of Beijing. And there we were talking about science and collaboration. The first connection between Australia and China in the modern era came from astronomers. An astronomer named Chris Christensen came here and worked on radio astronomy. And that paved the way for opening up of diplomatic relations 9 years later. Today, I am here visiting partially to be with my Prime Minister, but partially to work with my colleagues here in China on the new questions of astronomy, 3 of which are here. So these questions are, what are planets like beyond our own solar system? There may even be a planet in our own solar system we do not know about. What is the life history of the universe? And what is this stuff we keep talking about called dark matter and dark energy? Those are 3 questions I'm going to talk about today, and how we're working, and working often together to solve. So, let's talk about planets. We have 8 planets going around the sun. There may be a 9th one that we will discover, or there may not be. Pluto remains a planet in my heart, but not in the official heart of the International Astronomical Union. And so there are amazing leaps forward being made in understanding planets. In 1995, there were no planets known. This is the catalog of planets today. There are right now 2,107 planets confirmed beyond our own solar system. When I moved to Australia in 1995, 0. All of those have been discovered in the last 20 years. So how do we find planets? Well, there's a number of techniques we can use. One is by their motion. So when a planet orbits its sun, the sun also orbits the center of mass between the planet and the star. And so that means if you're looking at the star and we look at its spectrum, that's the light that it puts out, the fingerprints of every element leave little traces. And those traces move back and forth due to what we call the Doppler shift. That Doppler shift is something that affects all waves, and it's what gives the change of sound of an ambulance or a police car as it travels past you. It also causes the color of light to shift. Now that color of light shift is very tiny in the case of planets moving around their sun. So in the case of Earth moving around our sun, it's about 1 meter per second. 1 meter per second is this fast. But with modern equipment, like this installed in Europe in a very high precision spectrograph, we can measure speeds now about like what I'm walking. And that's to stars whose light takes 1,000 years to reach us, traveling at 300,000 kilometers per second. So those stars are 300,000 kilometers times 31 million seconds per year. That's a number most of you probably don't know. Times 1,000 years away. And yet I can measure that they're moving this fast due to technology. That is amazing. And that is what has allowed us to start discovering large numbers of planets. But it's not the only way we discover planets. With modern technology, we can correct the blurriness of the atmosphere with lasers. And that means we can make really good quality images from the ground now with telescopes much larger than the Hubble Space Telescope. And so we get clearer images. And that means we can start seeing planets for the first time directly. So here's how adaptive optics works. You essentially make a contact lens or a pair of glasses. You look at what the atmosphere does, and you bend a mirror to do exactly the opposite. And when you do that, you can see your image goes, in this case, the planet Uranus, goes from being fuzzy to looking much, much better than you can see it with the Hubble Space Telescope. And that's from the ground. With this technique now, we are able to, for the first time, see planets. Here is a star with 3 planets around it, and you can see them start orbiting. But this is just the beginning, because we're building a new generation of telescopes, much bigger than previous ones, and with looking at different parts of light. So this, what we call the Atacama Millimeter Array, or ALMA, this telescope is able, with radio waves, to look at stars. In this case, a star that's just recently formed. And you can see around the star there are little holes. It's looking at gas. And those holes, we believe, are caused by the planets going around and essentially vacuuming up that gas and forming and getting bigger. This is one of the most amazing images to me, because you are seeing a planet system being formed. That is this amazing telescope in Chile, located up at 5,000 meters. In the driest place on the planet. But this next generation of telescopes to come are potentially even more exciting. This is one of those new telescopes. I'll show you all 3 of them. This is known as the Giant Magellan Telescope. We hope it will be built in the beginning of the next decade, so about 2020. And it will use these laser systems, but this telescope is 25 meters across. And being so big, it will allow us to see these planets better than ever before. But that's not the only way we can discover these planets. Another way is something that some of you will have seen yourself a few years ago. I don't know what the weather was like in Beijing on this day, but in 2012, Venus went across the face of the sun. It transited that. It doesn't do it very often. Every 100 years or so, it does it twice. But when it does that, the sun becomes 1/10,000th fainter than it normally is, due to the shadow of Venus. If we go out and we look at thousands upon thousands of stars, we can see this happen occasionally, and we have started doing that. And we can use little telescopes on Earth to do this. For example, I am part of a program that uses a set of telescopes in Australia, a set of telescopes in Chile, and a set of telescopes in Namibia, so we can always see the sky. And we keep looking and looking and looking, and we look for those little things getting fainter. And so here was our first discovery. We found about 35 planets now this way. You go through and you see suddenly the star gets a little fainter. That's when its planet goes in front of it. An eclipse, so to speak. Now, we can do this in the ground, but you can do it much, much better if you get above the atmosphere. And the Kepler Space Telescope has been doing this. And it has literally discovered thousands upon thousands of objects. Here's its latest set of planets. Not all of these are confirmed, but there are 4,696 planets it's discovered, of about 2,000 of which are confirmed. And you can look, and it's how long it takes for the planet to go around its stars. 10 days, 100 days, 365 days is Earth. And the radius, how big the planet is relative to Earth. So I have conveniently put Earth on there, Jupiter, Neptune. And you can see we have already discovered something that has 365 days and the size of the Earth right there. Now, is that exactly the Earth? No, because it was not going around the sun. But it is almost impossibly difficult to find Earth with this technique. It's very easy to find very big stars that are close to their suns, and very difficult to find Earths, because Earths are small and they're a long way from their star. Yet we've already found one. From this experiment, we can already say that the average solar-type star has an Earth-type planet going around it. The Earth is not unusual. It is typical. The average star in the sky probably has something more or less like the Earth going around it. So that means that if we want to go out and find a new home after we've destroyed our own planet, or it destroys itself, we have a lot of opportunities, but we'll need to do our homework. And doing our homework is what astronomers are doing for you. How? We're putting new, bigger telescopes in orbit so that we can find around nearby stars Earth-like planets. And when we do, we can do something remarkable. We can use these new generation of huge telescopes to look into their atmospheres. How? Well, let's look at Venus when it went in front of the sun. You can see, this is a real picture. This rim, that's not Photoshop. That is light from the sun going through Venus's atmosphere and being bent, refracted through the atmosphere and traveling to us here on Earth. When that light travels through Venus's atmosphere, it picks up the fingerprints of Venus's atmosphere. So we can, if we have enough light, figure out what is in Venus's atmosphere by looking at how, when Venus is in front of the sun, how its fingerprint of his atmosphere suddenly appears. And to give you a sense how this might work, this is going to be the largest of the next generation of telescopes built by the Europeans, 39 meters across, assuming they save enough money. The less money they save, the smaller the telescope is, but it's still a very large telescope, 39 meters across. That's the scale of this entire auditorium. Everything manufactured to be in one place to 10 nanometers. Amazing technology. But it can potentially pick up the fingerprint of Earth-like planets around certain type stars. And to show you how it works, here is our sun. Each one of those little dark spots in the color of the rainbows is the fingerprint of an atom. That's hydrogen, that's sodium, and that's the stuff that's in the sun itself. But if you look very carefully up to the corner of up here, those little bands are not in the sun. That's the Earth's oxygen. And so if the Earth went in front of the sun, that fingerprint of light would be imprinted on the sun to an alien civilization looking at us. We can do the same thing with these new giant telescopes because they can collect so much light, they can see the tiny effects, in principle, caused by oxygen in the atmosphere. So I think that's pretty exciting, but it's not the only thing we're doing. We're also going to be able to tell the life history of the universe. So to do that, we need to understand a little bit of how our universe works. So to do that, we're going to go back to 1929 when Hubble went out and he made this diagram. He looked at how bright stars were in nearby galaxies. So if the brightest stars were bright, they're here. If they were faint, they're over here. And he knew that the further an object was, the fainter it appeared. So he said, these are the distant objects, and these are the nearby objects. He also noticed that you could measure how much their light had been stretched by the Doppler shift. He thought it was the Doppler shift. It's not the Doppler shift, it turns out, but it's effectively the same thing. And so objects that from the Doppler shift don't show any motion down here show a lot of motion at the top. And you can see the further away, the faster the motion. And the motion's always away from us. Things are redshifted. Their light is stretched red. So from this, he announced to the world in 1929, this means the universe is expanding. Now, why did he say that? Let me show you a cartoon. Here's the universe, or at least a cartoon version of it, which I'm going to expand. So I've expanded the universe. And now let's see what happens when I compare before and after. So when I compare before and after, I can see effectively what happens. So nearby objects, when I have overlaid the two, well, they've only moved a little bit, hardly at all. So if I was measuring how fast they were moving away from us, it would be a little bit. And if I look a long ways away, well, those things have moved a lot. You can see when I expand the universe, nearby things move a little bit, distant things move a lot. Just what Hubble saw. And it doesn't matter where you are, everyone in the universe sees exactly the same thing. Now imagine the universe is expanding. Let's run it into reverse. What happens? Things get closer and closer and closer, and there is a time when everything in the universe is on top of everything else, the Big Bang. If the universe is expanding, it's sort of a natural expectation of what the universe will be like in the past. So that means that when I take the Hubble Space Telescope and I take a very, very long exposure, a long picture of the sky, so in this case, a piece of sky much smaller than the moon, we zoom in and what do we see? We see 20,000 galaxies. And we're looking back in time. We're looking back almost 12.5 billion years in time. Because as we look a long ways away, it takes light time to get to us. And it takes light here 12.5 billion years to reach us. But when we look back 12.5 billion years, we're looking to a very different universe. We're looking to a universe that was 7 times scrunched compared to now in all 3 dimensions. And if I scrunch something by 7 times, that means that each piece of space is 7 times 7 times 7 times more dense than it is right now, or almost 350 times more dense than right now. And the universe looks different. The galaxies there don't look like they do now. Now we think if we look even further, we will see a time potentially before there are any galaxies, before galaxies had formed after the Big Bang. And to do that, we want to build a new telescope called the James Webb Space Telescope. This is almost completed. It will be launched in 2018, we hope. And this telescope will be able to look back to what we think will be the first stars. And so we think the picture it takes will look like this. And these little dots here, those are the first stars being formed. We'll see what nature really looks like when we get there. This is what we think it's going to look like, but we will not know until we look. But of course, we will have, for example, these third of the giant new telescopes. This is the telescope that China is involved with, the 30-meter telescope. It will be able to look at the objects this space telescope pinpoints and study them in detail and say, what were the first stars like? Did they form giant black holes? How did they form? How many formed? When did they form? Now, I'm impatient. And there's other ways we can learn about this time. If you go back earlier, when the universe was 10 million years old, this is what it looked like, nothing. But if we wait a little bit, we can use radio telescopes to get a different view. Whoops. I should say that if we go back even further with radio telescopes, we see the universe when it was 380,000 years old. At this time, the universe has been scrunched so that it is 1 billion times denser than it is now. And it's 1,000 times hotter than it is now. So the whole universe glowed like the sun. And we see this afterglow of the universe after the Big Bang, 380,000 years after the Big Bang. But I can keep squeezing the universe by just going earlier, but I can't see it. I have to think about it. And if I say, imagine I scrunch the universe even more, it becomes hotter and it becomes denser. And at some point it becomes so hot, nuclear reactions occur. And so one can go back to when the universe was 1 second old. Then the temperature is 10 billion degrees. That's hotter than the center of the sun. It's not quite as dense as the center of the sun, but it's so hot the nuclear reactions really can't even get started because they destroy themselves. But soon after that, as the universe cools, the nuclear reactions start. So we think the universe is full at this time of protons and neutrons, and then as it cools, those protons and neutrons can get together and make helium. But before they end up getting too far, the universe cools so much that all of the protons and neutrons are converted into helium and hydrogen. And these nuclear reactions are known extremely well here on Earth. So we can actually calculate that the universe should be 75% hydrogen and 25% helium. And when we go out and we look, that's exactly what we see, quite remarkably. Before this, well, things get hotter and hotter, and at some point we go beyond what we're able to create here on Earth. So the Large Hadron Collider at CERN provides the most intense temperatures on Earth. That's sort of about a microsecond after the Big Bang, and before that, we have to start guessing. But we can use the fact that the first stars in the universe should be made out of hydrogen and helium and nothing else. So there are 100 billion stars in the Milky Way, and we can go out and use a telescope we built in Australia called SkyMapper to identify those stars that have no iron in them. Iron has a fingerprint that's relatively easy to identify. And so we have just started our program, but we have already found something very interesting with this very large digital camera. And that is this star. This is the first star that has no iron in it at all. It has less than 30 million times less than our sun. And so the way this works is this is the fingerprint of iron. This was the record in 1995, a star that was 10,000 times poorer in iron than our sun. This was the new record in 2005, a star that had 300,000 times less iron than our sun, and then our new object, no iron at all. But, interestingly enough, it has carbon. This is the fingerprint of carbon. Now, there was no carbon in the Big Bang. What happened? Well, we think this is not a first star, it's a second star. And a second star was produced from a first star that produced no iron. Now, we think most stars should produce iron when they explode as supernovae, unless they form giant black holes. So one of the surprises earlier this year was the discovery of gravitational waves by two big black holes orbiting themselves. In order to have had a reasonable chance of discovering those two black holes merging, there must be a lot of black holes in the universe. So maybe this is a sign that the first generation of stars produced a lot of black holes. That's a guess. We need to find out what really happens. That is something we're going to learn about in the coming years. So this is one way to do it. Another way is to put a satellite in space and literally look at billions of stars. And this satellite done by ESA, known as Gaia, is doing that right now. It is mapping out 1 billion stars and asking very precise questions about what each one of those stars is made out of and how it's moving. So the idea is we might be able to figure out how the galaxy came together, star by star. All right. Now, I said earlier that the universe went through this dark period, a dark period before stars. And that's true, but the universe would have been glowing, it turns out, in radio. And that's because hydrogen glows in radio when it's cold. And so we might imagine that the universe looks something like that when it was 100 million years old, caused by the first stars. So why does hydrogen glow in radio? That's because within an atom, protons and electrons have spin. And when they're aligned, the atom is in a different state than when they're not aligned. And if it changes, then it turns out you get a radio wave, one at 1.4 gigahertz, or something not dissimilar to what your phone uses to communicate to the tower. Now, that single photon is very, very faint, but there's a lot of hydrogen in the universe. So if you build ginormous telescopes, you have a chance of seeing these things, but you need to go to a place that is completely free of electronic interference. And for those of you who have ever been out in the middle of Australia, you realize that your cell phone does not work. So here, in the middle of Western Australia, in the desert, we are building a prototype telescope to look for this hydrogen in the early universe. Now, this telescope looks a little different than most telescopes. Normally, to make a telescope focus, whether it be radio or optical, you need to have it be the shape of a giant parabola. But with modern electronics, you can actually use computers to make the parabola in software. And that means instead of having to build giant telescopes, you can cheat. But it's right on the edge of technology. So we are working with this array called the Murchison Wide Field Array in anticipation of the next generation telescope called the Square Kilometer Array. The Square Kilometer Array will be built in southern Africa and Australia, and it will hopefully eventually have a huge 1 kilometer by 1 kilometer scale. Now, you in China also know how to cheat and take shortcuts to making giant telescopes. And this is your telescope, known as the 500 meter across radio telescope, or FAST. This is using the landform in the center of the southern part of China. It's being finished this year. And so by using the landform, you can make the telescope very, very large. So this telescope will be able to see deeper into the universe in hydrogen than anything else when it is built. It will also be very good for looking at other things like pulsars and potentially whatever happens when these black holes merge that make gravitational waves, we might hope to be able to see that with this telescope as well. So this is a very exciting telescope, much bigger than anything else ever built, and an amazing piece of technology, but it will be very challenging to get it working perfectly, I promise you. All right, so my final session is, what is this stuff called dark matter and dark energy? So before I answer that question, I better tell you what dark matter and dark energy are. So I'm going to tell you about our discovery, which led to understanding dark energy, and I'll also explain dark matter along the way. So we remember from Hubble, saw that the universe was expanding. But imagine I want to understand what that means. So an expanding universe means that the separation